So it's my great pleasure to introduce Anthony today for the second speaker of the day. First, a short, procedural stuff. If you do have questions, you actually can submit them online if you're viewing virtually, or if you're here, you can also submit them via the app. We'll see them at the table over there, and we'll read them out if you feel more comfortable to just submit your questions online or via the app. So Anthony Maschia is a well-known physicist for everyone here. He received his master's and his PhD at the David Geffen School of Medicine at UCLA, and is now an associate professor at the University of Cincinnati and the director of medical physics at the Cincinnati Children's Hospital. In that role, he has the wonderful machine to play around with a lot of proton flash and will tell us all about it. Thank you.
Okay, good morning. My name is Anthony. I'll be talking about the proton modality track and proton flash. These are my disclosures. And a brief introduction. So one thing that's beautiful is that there's no competing session, so nobody can leave. You flew all the way to Toronto to listen to me. One of my favorite quotes from Groucho Marx saying, "I refuse to join any club that would have me as a member." So my corollary is, you should refuse to attend any conference that would have me as a speaker. But welcome, and I'll do my best. The outline for my talk is, I thought I would start with a clinical example in conventional proton therapy, and then move from there into proton flash and then future topics. The previous speaker, Dr. Kong, one thing I did appreciate was, there's no need to get rid of all the advantages of the existing modalities. Flash should be building on top of what already exists. A quick introduction to Cincinnati Proton Therapy Center. So as Dr. Schumann had mentioned earlier, we have this room that we get to play around with our flash machine. So this is our facility. We have 2 proton pencil beam scanning treatment rooms that we treat adults and pediatric patients all day long. And then we have this research gantry that was installed at the same time. It was never intended to treat humans on a daily basis, but it was a dosimetric clone of the 2 conventional rooms. And so it was retrofit to be our flash room. The Proton Therapy Center is a Cincinnati Children's Hospital in partnership with the University of Cincinnati, and that's our flash room. So that's the room that we conducted FAST-01. It's the room that FAST-02 is open in, and it's also the room that we do all of our preclinical and translational studies in. So proton radiotherapy conventional. For some people in the audience may not be as familiar with conventional proton therapy. And this patient is actually under treatment in Cincinnati right now. And so I think this is a good example of where I think proton flash could be going to take advantage of the flash sparing properties. So protons spare healthy tissue very well. You can see that the contralateral kidney is basically no dose. But with neuroblastoma patients, it's not uncommon that the ipsilateral kidney is very difficult to spare. Protons do a very good job of sparing everything else, bowel, liver, at least parts of the liver. But the ipsilateral kidney is hard to spare. This is because protons rely on physical dose distribution. But this can be at the cost of range uncertainty, LET or RBE uncertainty, motion, robustness. There's a lot of other concepts I don't have time to get into. But I think the begging question when this came through peer review is, could flash spare more? And we'll get back to that later. So proton flash radiotherapy. This is just to compare it to the other existing modalities. You can see that the Bragg peak stops in a medium. So there's no dose delivered after the Bragg peak. But for proton flash, we have 2 types. One is transmission beam flash. The other is spread out Bragg peak flash. And these were alluded to earlier. Right now, all of our FAST-01 and FAST-02 are transmission beam flash. And then you also have kind of a synergy with existing proton therapy techniques that are both scanning and scattering. And so when you look at the technological roadmap for proton therapy, you see sort of a synergy between, let's take, for example, pencil beam scanning and ridge filters. So ridge filters were developed decades ago for passive scattering, but you see them sort of making a comeback because they can give a static SOBP. So just a brief summary of what is FAST-01 and FAST-02 to get to kind of show where we have been and where we are as of today in proton flash clinical trials. So this is FAST-01. It accrued for about a year, treated 10 patients. It was published last year, and it treated extremity bone mets. So we treated humerus, femur, tibia. The results were published, and it wasn't powered to show that flash was better. It was a single arm. It was really a feasibility study to show that, yes, you can do this in a clinical environment. FAST-02 took a step, the next step forward was FAST-02, which treats thoracic, non-vertebral body bone mets. You can see our first patient there treating a rib met. The big difference in technology between the two was FAST-01 was static rectangular fields, and FAST-02 you can treatment plan. You have a beam's eye view, 2D, I would call it 2D conformal transmission beam. The planning system has some prediction of the dose rate, and you can compare this to your patient QA. So FAST-02 did take a step forward technologically. It still would be a feasibility study in treating targets of the thorax. So, but what's next? FAST-02 is 40% accrued. It'll continue to accrue until we have 10 patients. And then, what's next? I think that's what we're all asking ourselves. In terms of, I have a few topics I want to touch on that at least I felt like we learned through FAST-01 and FAST-02 and maybe pointing a little towards the future. Let's see here. There we go. So I do want to introduce two important collaborators for Cincinnati. You see a picture here from Dartmouth University using fast cameras to image dose rate. So one of the limitations of clinical trials is how do you do quality assurance? And existing detectors aren't great at measuring ultra-high dose rates, but these cameras are. And so it's a partnership we formed with Dartmouth, and they retrospectively QA'd all of our FAST-01 fields and compared them to our log file. Our log file of the machine was our ground truth, but you could see how that's kind of a circular argument that the log file that's part of the machine is telling you everything's safe, but you want something independent of the log file to say everything's safe. Our other collaborator was the National Physics Lab in University College London in Great Britain. They have a graphite calorimeter that sort of QA'd and our reference field to make sure that we could, in fact, calibrate dose. So these are some examples from FAST-01 and FAST-02. These is FAST-02 data. There's a presentation later this morning that'll give more detail. But you can see we're delivering 1 × 8 and measuring variation as a function of Gantt angle and measuring the dose. So the dose was very stable, again, cross-calibrated to a graphite calorimeter. And we used in collaboration with Dartmouth, QAing the log file against an independent measurement check. And those will be presented at 11:30 today. And so this is the data that our ion chamber methodology compared to a calorimeter is dead on. It's a couple tenths of a %. And so one controversial opinion, at least I've found, is I think in the current therapeutic range of dose rates, if you select your ion chamber and electrometer properly, you can calibrate a flash beam. You can calibrate the dose. It's well known and well studied, well understood. And there's publications coming out on this. I think that's not true for electrons. It's not true if you go to 1,000 gray per second. But I think within the realm of what we would define proton pencil beam scanning dose rates at, say 40 gray to 120, 150 gray per second, I think that this problem seems to be solved. I just thought I would advertise and talk about an intercomparison that we're running through the Flash Forward Consortium, looking at can multiple institutions that are all flash enabled calibrate their dose and compare to each other and be monitored by independent parties. This is important on a clinical trial as well, to make sure that if it is a multi-institution clinical trial, is everybody calling their flash dose and dose rate exactly the same? These are the participating institutions. It's a large study. I vastly underestimated how long it would take to get 10 institutions to mail detectors all over the world and cross-calibrate their flash machines. But nonetheless, that study is underway. The preliminary results, I worked closely with the group in Aarhus, their Proton Therapy Center, and we blindly measured, calibrated our machines, and had OSLDs, TLDs, and alanine mailed from IROC, NPL, PSI, and DTU. And we compared all of our results. And our results are very good. It's, we're all within, kind of max to min is within, say, 1.5%, 2%. So I think this also further validates the ability for us to hold clinical trials, not just single institution, but multi-institution clinical trials, and monitor them. A slight detour on the dose rate question is because we're using pencil beam scanning and the preponderance of data is using electron beam, quantifying the flash effect, are we sure that the pencil beam scanning dose rate definition actually has a flash effect correlated to it? So this is unpublished data. We're working on publishing it. We took one of the FAST-01 fields, a 7x10, and we irradiated a whole mouse. One fraction, one beam, we gave 9 gray, a little bit more than what we gave on FAST-01, mostly to try to hit the LD50 for a whole mouse. And we delivered 1, 25, and 55 gray per second as defined by the pencil beam scanning dose rate. It's a small study, just 5 mice per group. But when you look at survival, it's very clear that the pencil beam scanning dose rate, as defined even at 25 gray per second and 55 gray per second, has a survival benefit over conventionally defined beams at 1 gray per second. This also points to at 25 gray per second, we see a flash survival benefit. Now, it's survival, it's not looking too deeply. But that may mean that does the instantaneous dose rate, which is much higher than the voxel-based dose rate, does that matter? Is that what we should be looking at? But nonetheless, if you take the definition of dose rate on FAST-01, you apply it to this study, you see this survival benefit. And you do see, this is on the left is a blood draw just looking at hemoglobin, red blood count, white blood count, platelet. And you can see at least some differential effect between conventional and flash. So this at least convinces us that the pencil beam scanning dose rate that it has a flash effect correlated to it. So looking at technology, and this was alluded to in the earlier presentation right before mine, where is proton therapy, flash technology going? And so I talked to some of the vendors, and I thought I would just show some of the directions of technological development, of course partnered with many institutions. And I think one important piece is, well, why is IMPT as it is now maybe not good, well suited for flash RT? And I think the simplest answer is layer switching is too slow. So the layer switching, depending on the machine, can be maybe 1/3 of a second, 1/2 a second, some are more than that. And if you have 4, 5, 10, 15 layers, you're already looking at a time scale that's way too large for the flash effect to be seen. And so there's a technological development that needs to be made in that case. Shoot-through beams do not take advantage of the end of the Bragg peak, where you can spare healthy tissue. You can get a very high dose rate because there's no scatterers, there's no beam spoilers, so the dose rate's preserved, but the conformality is sacrificed. And is this a problem or not? And so one solution is to come up with sort of ridge filters. You'll hear different terminology for the similar device. But can you use a range shifter ridge filter to kind of create a static SOBP and modulate the range to get conformality? And I think you'll see similar threads through the community in terms of technological development. This is another example, if you can see on the left, second picture from the left. That's what at least one version of a hedgehog or a range filter looks like. That device is creating an SOBP in lieu of layer switching. A future flash machine may be something that has fast enough layer switching, that has fast enough scanning to actually see a flash effect with pencil beam scanning. That would be sort of an idealized proton therapy pencil beam scanning flash machine. But at this moment, I think it's not quite there technologically. And so this sort of begs the question, does Bragg peak flash replace transmission beam flash? Is there this conflict between Bragg peak and transmission beam flash? My editorial would be, I think it's far too early to say. I think it's the wrong time to decide what machine we need. And I think that's because it's not well studied and well understood. Every technological iteration will have some limitation. And so does Bragg peak flash have a field size limitation that doesn't exist for transmission beams? Or is there tumor limitations, dose rate limitations? Anytime you spoil the beam with a scatterer, you're going to reduce the dose rate. And so for the same beam current, you'll have more dose rate for a transmission beam than you would for a scattered beam. Does this impact robustness? One thing you heard of here for proton therapy is there's range uncertainty, and there is in fact range uncertainty. There's a calculation about where does the proton beam stop, and there's some uncertainty related to that. But does flash solve that problem sort of coming from the back end? I mean, range uncertainty is a problem because in the clinical practice, it means you're treating more healthy tissue. You're treating more OARs in order to ensure you're treating the tumor. And if you treat more of the OAR, you get increased toxicity. That's sort of classic radiation oncology. But if flash reduces toxicity, do you need to worry as much about range uncertainty? I think that's a fundamental question that has to be asked in the clinical trial pathway. And then is Bragg peak flash feasible? I mean, we heard just this morning that Bragg peak flash is being used at UPenn in their facility. Can it be used for large tumors, small tumors? What is the overall feasibility in a clinical space? And I think most importantly, at least as a physicist, I like to reverse engineer problems. So what do we want to treat, and then what do we need to develop? Not necessarily what do we want to develop and then try to find something to treat. Spoiler alert, one of those guys is Darth Vader. All the physicists know, I'm sure. So, earlier alluded to, I think the community understands that this is a question that's important, is multi-beams and multi-fractions. Flash spares healthy tissue, fractionation spares healthy tissue. First, disclosure, I'm a physicist, so when I talk about biology, that's a bird to me. There's no other anatomy, that's simply bird. So if you ask biology questions, I'll defer. But first, I mean, publication that's well known, already presented in the previous talk. I think this is the type of study that we need to look at, is can we get the fraction size down? Because we know fractionation spares healthy tissue, that's why we do it in the first place. So can we get an enhanced sparing effect on healthy tissue as we fractionate with flash? And then there's even a more, sort of another problem that isn't necessarily fractions, it's beams. So if each beam is its own session, you lose the flash effect or maintain it as you break up one fraction into smaller pieces? So you have the prescription dose, you break it into fractions, and you break every fraction into beams. So in Cincinnati, we did this study looking at, from the Sartorial lab, irradiating the hind leg of a mouse. And this is, there's a lot of data going on here, but I try to keep it simple. Let's just look at 35 gray. You see a flash effect between conventional and flash. We all know that would happen. But then if you take that same 35 gray and you deliver it 1.5 to 2 minutes apart, so you deliver one beam of 35 or 2 of 17.5 or 3 of 11.7, what happens to the flash effect? And at least in this model, you see the flash effect being diminished as you treat more beams per fraction. We see the same thing if you look at, this is comparing conventional and flash. By 3 times 11.7, you don't see any difference between conventional and flash. And so is this something that we observe in clinical practice? This is critical because there's very few modalities that are going to treat deep-seated tumors with one field. Proton's probably maybe the only modality that can do that for a deep-seated tumor. And so you see this kind of multi-beam separated by a couple minutes, which mimics the clinic, has an impact on the flash effect. And so all of this needs to be on a preclinical translational study to inform our clinical trials. And I just bring this up as a historical footnote that for people, particularly in proton therapy, figure A, that was not uncommon to treat prostate patients with a single field. You'd plan it for 2 and treat 1 field a day. So you treat the left lateral one day, right lateral the next day, left lateral the next day. That wasn't uncommon 15 or 20 years ago. It was, we kind of went away from it because of dose of the femoral head. getting a higher dose per fraction and then missing a day, and the radiobiology of that wasn't clear. But if flash is effective, can you come up with a 2-beam flash plan that treats one beam? If the beams matter, treat one beam one day, treat one beam the next day. Can you do that? I'm not advocating I'm not saying low-risk prostate patients are what we should be treating with flash, but I'm simply using historical footnote sort of conceptually for how should we move flash forward. And I do think that protons are probably one of the few modalities that can treat a deep-seated tumor with fewer beams if the number of beams matters. And then there's I'm sort of a pragmatist. When I look at a practical clinical operations and say, you have a clinical schedule that you're treating a bunch of different patients on one schedule, what modality can treat all of these things? Or are we going to have separate machines for separate cancers? Maybe we do. Maybe that is the way it goes. But if you're treating something that's shallow and deep, hypofractionated, single fraction, multiple fraction, moving target, stationary target, and you need to minimize the beams, but you also want to leave room for flash, for grid therapy, lattice therapy, mini beam therapy, intensity modulation. I think there's a desire and a need to kind of engineer a machine that can do at least as many of these things as you can. So you're searching for this kind of Swiss Army knife in terms of the device we're going to use in the future. Now, there might be a device, and maybe that's not what happens. Maybe what happens is you do have a flash machine that's VHEE, and you have an intensity modulated proton therapy system in the next room. Maybe that's what happens. It's unclear at this point. It's also why I think it's not the time to necessarily cancel or pick a machine. I think there's still a lot of need to define what these machines are capable of and what are we trying to treat. So to bring us back to that example I showed at the beginning, that 3-year-old we're treating in Cincinnati right now, that's what a transmission beam would look like. You can see I'm treating more contralateral kidney, treating more liver, but does the sparing from flash overcome that if I can get the number of fractions down? This would be a single beam. Does Bragg peak flash? That looks much better. So you think, well, that's giving me all the benefit of conventional proton therapy, but I'm also, if you look at it's an orange circle, that target, the ITV is the orange drawing, and you can see it's surrounding the ipsilateral kidney. I think the only way to spare that ipsilateral kidney is with flash. I don't think that the physical conformality, you could also do a 10-beam IMPT plan if you wanted, make a very complex plan that may not be very robust. But if you want a robust plan that you can deliver in a clinic, it may be the only way to spare that ipsilateral kidney is flash, because you're not going to spare it with physical dose distributions much better than it already is. And so conventional RT, proton RT, spares the OARs, but I think flash RT could spare the healthy kidney. And I think that's the kind of example we hope to use in Cincinnati to drive our clinical trial pathway forward and inform our preclinical studies. I mentioned earlier, does flash help you manage LET and range uncertainty induced endpoints? Moving targets. A 3-year-old can't do breath hold, but an adult can. And if the beam's on for half a second, it's really easy to hold your breath for a couple seconds and treat the patient. And then we have to understand better our field size and target complexity challenges. Before pencil beam scanning, it was uncommon to treat a bilateral head and neck with proton therapy simply because it was hard to create an aperture compensator pairs to do such a thing. And so is it going to be hard to treat a bilateral head and neck with ridge filter proton flash? Maybe you still need IMPT. But if IMPT natively can be flash, then you have a great device. We have to keep looking at those fewer beams and fractions, and is it better than standard fractionation? I think a question just earlier was, how do you construct this to compare standard fractionation with flash fractionation? If you're using a BED calculation to determine what your hypofractionated regimen is, you might be wrong right off the bat. And I think it begs the question with spatial fractionation, flash RT, intensity modulation, IGRT, what is the machine of the future? And there's some balance between discovery and engineering. So for conclusions, I think I demonstrated that protons spares healthy tissue. Flash may be able to do even more. We shouldn't eliminate the current advantages of RT modalities. We should use flash to build on top of it. And all those topics should be informing our clinical trial pathway forward. There's certainly exciting work ahead. These are all my acknowledgments, and thank you very much for your time.
Thank you very much. That was a very interesting talk. Any questions from the audience? Please use the microphone.
Really nice talk. I wanted to add another comment, really. Most of the tumor volumes that we irradiate with flash are always very small. As soon as the volume increases, you have a major problem with volume, right? First, you cannot achieve high dose rate with big volumes, then you have all the side effects, which are a problem. How do you think we're going to get around it? Because I don't think Bragg Peak or Shoot Through are solutions for this problem.
Yes, I think if you look at where the clinical need is, I think large targets are often where the need is, but then how do you get the technology to line up behind the need? I mean, one option is pencil beam scanning. If you buy that the pencil beam scanning sort of a voxel-based dose rate does have a flash effect, and at least we have some limited preclinical data saying it does, then the size of the tumor, I mean, for FAST-01, our biggest field size was 7 cm by 20 cm. And that's because you rely on a pencil beam scanning dose rate, not sort of a constant fluence dose rate. So I think the way around, I think the larger targets, I have seen some presentations were showing that sort of a scattered or ridge filter proton flash can get up to 10, 12, 15 cm, something like that. But if you want to go even bigger, maybe it is pencil beam scanning that has to be done. That would be my answer.
And that was Joao Seco asking the question. Next, MCAT.
Yeah, Maria-Catherine Vosnin, Geneva University Hospital. Thank you, Anthony, for the wonderful talk. I have one quick question and another more a comment. I really like your data on the metabolic system. That's really super cool type of data. Have you done dose escalation? Have you been able to define a dose modifying factor on those type of experiments?
Right now, all the clinical trials are not dose escalation, just a single dose.
I'm talking about the mouse data, the 9-grade total body.
Oh, no, I gotcha. We chose, it was a small experiment. We were getting hammered by referees when we submitted papers. That's the honest truth, is saying, how do you know this pencil beam scanning dose rate has any flash effect at all? So we chose 9 simply as an LD, because it was a published LD50 for the mouse. But we do have interest in, I have some interest in going lower as well, and then going higher. And we feel the same way with dose rate, trying to bring the dose rate down. We defined conventional dose rate at 1 grade per second, but it's been really interesting. Last FRPT, I believe the group from our house presented, they use a lower conventional dose rate, which actually impacts the dose modifying factor. Their dose modifying factors are higher than us. I don't think it's because the flash effect is bigger, but because the denominator is smaller. So, but yes, so I think that's right.
And now the comment. You were talking about a sort of reverse engineering, like trying to build the ideal machine to answer the question, and then I got confused because at the end you do what you can with what you have. And for instance, with the data on the multi-beam study, there is a big question to be answered. What about if you were able to raise up your dose rate doing this multi-beam? Here you were very limited with the 100 gray per second. You lose the effect, but only with 100 gray per second. Yeah.
Everything you said is right on the money. I couldn't agree more. To me, especially as like a clinical physicist, I always think there's what can I do now, and what do I want to do in the future, and then what kind of overlaps. So I always feel kind of conflicted about. I mean, FAST-01 and FAST-02 are sort of skewed towards the pragmatic. We have a machine. This is what we can do. We should get that going. But then I think there is room for the basic discoverers to say, we have this new thing that isn't in the clinic, and maybe we should be doing both in parallel. I kind of have more of an engineering mindset, like take one step. I'm not necessarily a giant leap person, but I think both of them are important. I think you're right on the money. So,
next question by Charles Lemoli.
Charles Lemoli, UCI. So nice talk, Anthony. So
thank you.
We're going to squabble a lot about fractionation schedules at this meeting. And the data that you showed where you separated the beam by, what was it, a couple of seconds or something?
A minute and a half.
Minute and a half, and then you slowly lost the flash effect.
Yeah.
And then now, so that's very different than the study we did, where we're doing once a day.
Yes.
So this begs the question to the entire group, right? And so I understand the clinical reason for this, and even sure, you got to move the beam to a different spot, you got to pause the beam for a bit, or if the damn thing breaks down, you got to come in from another angle. But lots of people are talking mechanism, and so the other advantage of separating the time, maybe over the course of a day, is to reduce overall treatment time. You can do that a couple of ways, right? Jack the dose up per fraction. But no one's done the experiment where they've taken 4 or 5 published hypofractionation protocols that have been shown to do dose sparing and separated it by 2 hours in 1 day to see if sublethal damage repair makes a difference. So that's a critical experiment we're waiting on. Now, I have a pretty good idea what's going to happen, but I'm going to wait on that because I think that's going to really point to whether DNA damage and repair has a lot to do with this.
Thank you.
Point well taken.
There's
A very nice explanation where are the limitations of the present facilities. It's absolutely correct, whatever you were exposing. I would like to advertise my talk today at 4 o'clock because I'm solving Oreo problems in the proton therapy. The way I solved it is the magnetic field is not changing at all for any energy range. So you can do the delivery in 100 milliseconds of 40 grays. So this is the only way to solve the problem, accelerator type.
All right, thank you.
Thank you for the very nice talk. I'm Steven Heijbraak, Holland PTC Proton Therapy Center in the Netherlands. And well, your experiment gives a very nice illustration of the relevance of the PensaBeam scanning dose rate. I was wondering, did you also look into the spatial distribution of PensaBeam scanning dose rate or other dose rate definitions in these experiments, or not yet?
No. No, I think that's a good comment. We assumed that we know that the dose rate varies across the field, especially a 7 centimeter by 10 centimeter field. What we called, the dose rate published there is central axis dose rate, but I think you're right to say that it varies across the field.
Yeah, I would expect both dose rate and also the radiosensitivity may vary, maybe inhomogeneous in the mouse.
It does. I think I guess in my mind, in a relative study, the mouse is in the same, if there is a heterogeneous distribution of the dose rate, it'll be reproducible, and the mouse alignment's reproducible. So I think you're right to say we could go back and look at that distribution. I do have confidence that it's the same for all 15 mice, and so if there's something there, maybe we could tease it out.
Okay, if the setup is reproducible, that helps. Great, thank you very much.
No, thank you.
All right, one more.
Yeah, Marcus Schwarz from Seattle. Thanks for your talk. I agree with you that the debate shoot through versus conformal may have something to say when it comes to field size. I'm not sure about range uncertainty because the argument is with shoot through I don't have range uncertainty, or you have arbitrarily high range uncertainty by CM and CM. So one can always create a conformal plan which is somewhat more conformal. How do you see that?
I agree. I think if I was in a marketing department, I would say transmission beam has no range uncertainty. Yeah, because you're treating right through the whole patient. You're treating everything. So I totally agree with that comment. I think for conformal or Bragg peak flash, and I haven't studied it enough to say, I would say the range uncertainty is the same. It's not less. It's the same. But I think the range uncertainty, as a physicist, range uncertainty bothers me because I don't like uncertainty. But range uncertainty bothers a clinician because it irradiates more OAR. You get more OAR dose, and you get toxicity related to that. And so I wonder if you don't reduce the range uncertainty, but you reduce the effect of the range uncertainty for Bragg peak flash. This is what I'm thinking.
But range uncertainties are not arbitrarily high. We are not off by 100%. We may be off by 3, 4, right? So I can even say 5, okay, but
I agree with you. I think, I mean, in our facility we use 3.5%. So it's not, as you suggest, it's not centimeters. I think the only question in that case is if your tumor's close to a sensitive structure. A few millimeters in those cases, say a brain patient, in those isolated cases, that 3.5% could be a difference. I mean, for example, we see if you treat brain, we have a large population of central nervous system patients in Cincinnati. And if you go back over the publication record, 5 or 10% of patients get some brainstem necrosis from some radiation modality. And so I wonder if, and in proton therapy, you mitigate that by using multiple beams and trying to come from different angles and use 3 or 4 fields when you really could just use 2. So you have some strategy to mitigate it, but I wonder if flash would be an additional mitigator of that type of toxicity. That's what I think.
Thank you.
But thank
We
you
have
for the question.
One more question from online from Si-Young Kim. Isn't the scanning beam similar to multiple beams? You said you observed reduced flash effects with multiple beams. Don't you expect the same with scanning beams? Maybe because scanning beams deliver the full dose in each voxel? It's kind of a
That's a good question. I'd hesitate to answer because I don't have data. I'm a data person. So, but maybe a multi-beam, maybe somebody who has a passive scattering proton flash machine could repeat our multi-beam data and answer that question.
All right, well, in the interest of giving everyone more time to mingle, let's close the session. Thank you very much. We look forward to your mouse studies next year.